Morning, students. Mr. Carver here. Today is section 2.2, part 2, and this has to do with projectile motion. So in section 2.2, you've been deriving with all the shortcuts, but they also put this topic in here as well. And projectile motion basically models the height above the ground of an object when you toss it into the air, basically. There are two formulas that we're going to use, and they differ only by units of measure. So if we're using meters, the formula for position is P is equal to negative 4.9 T squared plus V sub OT plus S sub O. And again, that is for meters. And then, if we're in the US, we're going to be using imperial measurement. And if it's in feet, the position function is P is equal to negative 16 T squared plus V sub OT plus S sub O. Okay, so a couple of things about both of these equations. T is equal to seconds. V sub O is equal to the initial velocity, and then S sub O is equal to the initial height. Okay, and then I guess I should mention that P is equal to the height above the ground after T seconds, or at T seconds. A couple of things that I should also mention about these formulas is that velocity, actually they're all sign sensitive. However, it is important to realize that V sub O and S sub O are sign sensitive. That is, if you're throwing an object upward, V sub O is greater than 0, and if you're throwing the object downward, V sub 0 is less than 0. The same can be said for the initial height. If you're throwing it from a platform above the ground, S sub O is greater than 0. And if you happen to be throwing it upward from a hole in the ground, S sub 0 is negative, less than 0 rather. All right, let's take a look at a problem. Let's say that you throw a pumpkin upward at, let's call this 10 meters per second from the Royal Gorge Bridge, which is 320 meters above the Arkansas River. What you end up with is a position function that is P is equal to negative 4.9. This is going to be plus 10T. And it's going to be 10 because I'm throwing it upward from the initial height of 320. These are graphing calculator problems. So if we were to graph this using a window from, let's see, 0 to maybe 15 seconds along the x-axis, because that's the number of seconds rather it would take to fall from the bridge height all the way to the Arkansas River, and maybe 0 to, say, 400 along the y-axis. I'm picking 400 because I am throwing it upward from 320 meters, so it's going to go upward slightly before it goes down. You're going to get a graph that looks something like this. And again, you're going to have to play around with the window a little bit so that you see at least the portion of the parabola that represents the problem. Now, the reason these problems exist or occur in calculus is because if you think about the position function, it gives you the height above the ground after t seconds. But if I think about the slope of this curve, the slope of the position curve is the change in position over time. And if you think about change in position over time, that's really just another word for velocity or speed. For instance, your speedometer on your car or the speedometer on your car gives your rate of travel in miles per hour. That is change in position over time. So if I derive position, p prime, what I end up with is velocity. And I see that I left something off here. This should be t squared. So if I derive position, what I end up with is negative 9.8 t to the first. Remember, the power comes down to the front, and you take 1 away from the power, plus then 10. And this was t to the first, so if 1 comes down to the front, I get 10 times 1, then t to the 0, and that goes to 1. And of course, 320 derives to 0. So if I derive the position function, I end up with the velocity function. So for instance, if I wanted to know the velocity at 2 seconds, I'd take 2 and plug it into the t in my velocity function, and I would get v of 2 is equal to negative 9.8 times 2 plus 10, and that gives me negative 9.6. And in this case, it's going to be meters per second. Now, the reason it's negative is because at that time, the pumpkin is traveling downward. It's traveling toward the Arkansas River, which is why velocity in this case is negative. Now, similarly, if you take the change in velocity over time, the term for that is acceleration. So if I derive the position function twice, or if I derive the velocity function, what I end up with is acceleration. And the acceleration formula, in this case, if I derive the velocity formula, I end up with negative 9.8, and of course 10 goes to 0. And what I end up with is the gravitational constant for acceleration due to gravity on Earth. This is negative 9.8 meters per second squared. So to review, you take the position function, you derive it, which gives you a velocity function. If you derive the velocity function, you end up with the acceleration function, which in this case is constant. On some of the problems today that you'll be working on, objects will be dropped. So for instance, in this case, if I took a pumpkin and I dropped it from the Royal Gorge Bridge, what I would end up with is a position function that looks like negative 4.9 t squared plus 0t plus 320, because the initial velocity when you release the pumpkin is 0. Another question that might be asked about this pumpkin is, and again, let me redraw the graph, something like this. If I want to know the velocity of the pumpkin at impact, what we're looking for is the velocity just as the pumpkin impacts the ground. What I would do is I would take my position graph and find out how long it takes for the position to reach this point right here. So if you recall in your graphing calculator, there is an intersect option under the calculate, which is second trace. And the easiest way to do it, in my mind, is to graph a second function right here at y equals 0. So you've got y equals 0, and you've got your other function, your p function, of negative 4.9 t squared plus 10t plus 320. It is second calc intersect. You'll then choose the first curve and the second curve, and it will give you an x value right here of t is equal to 9.166. That is the number of seconds it takes the pumpkin to travel from the bridge all the way to the Arkansas River. If I'm looking, however, for the velocity, then I'll take 9.166 and plug it into my velocity function. So this is going to be negative 4.9 times 9.166 plus 10, which gives you a velocity of negative 79.827. And that will be in meters per second. So that should be enough to get you through most of the problems. I'll answer questions when I see you guys tomorrow. Thanks.